Good morning, everyone. My name is Jacinta Humphrey, and I'm a PhD student at Latrobe University. Today, I'll be discussing what drives patterns of urban bird diversity. Over the next 12 minutes, the global human population will increase by 1,700 people. That's roughly 3 times the number of delegates who normally attend the annual ESA conference. This rapid population growth is resulting in urbanization, a process which alters natural habitats by removing native vegetation and replacing it with human infrastructure. Urbanization is one of the leading causes of land use change worldwide and is considered a major threat to biodiversity. There is now a wealth of literature investigating the relationship between urbanization intensity and bird species richness. Urbanization has been quantified in a number of different ways, including human population density, housing cover, the extent of impervious surfaces, and even artificial light at night. Regardless of the method, the consensus is clear. Increases in urban development have a negative influence on avian species richness. At the same time, studies have also investigated the influence of habitat. Whilst the definition of suitable habitat varies according to species, some general measures include the presence of remnant native trees, the proportion of exotic vegetation, and overall tree cover. Collectively, these studies suggest that habitat has a positive influence on species richness. Studies to date, however, have often focused on one of these two variables in isolation. In reality, both housing and habitat vary along continuous gradients and are not necessarily inversely correlated. So this begs the question, what drives patterns of bird diversity in urban spaces? I aim to disentangle these two variables and determine the relative influence of human infrastructure and available habitat on avian species richness at the landscape scale. To achieve this, I selected a series of landscapes positioned along 2 spatial gradients, the first of which is a gradient of housing cover. To assist with landscape selection and stratification, I used the total number of houses within 100 hectares and grouped my landscapes into 3 categories: urban with over 1,000 houses, suburban with 400 to 800 houses, and peri-urban with 100 to 200 houses. In addition to these 3 housing categories, I chose to survey along a continuous gradient of canopy tree cover. I then selected a total of 30 study landscapes to fulfill these requirements, 15 of which included a waterway and 15 did not. My landscapes were located throughout the northern and eastern suburbs of Melbourne, spaced a minimum of 1 kilometre apart. They spanned a housing cover gradient of 9 to 39% and a tree cover gradient of 13 to 63%. Each of my study landscapes was circular, covering a total area of 100 hectares or 1 square kilometre. Within each landscape, I established 10 survey sites, spaced a minimum of 200 metres apart. Sites were allocated evenly across the area in proportion to the land uses present. At each of my 300 sites, I conducted a 10-minute point count to record all bird species seen and heard within a 40-metre radius. Overall, I conducted 5 survey rounds in a period of 16 months, from September 2018 to December 2019. In addition to my bird surveys, I collected data on the composition of my study landscapes using aerial imagery and ArcMap. I overlaid a grid of 200 points onto each landscape and quantified the percentage cover of housing, canopy trees, riparian areas, and open green space. Next, I digitized patches of surrounding native bushland within a radius of 1 kilometre, 1.5 kilometres, and 2 kilometres. These 3 radii were found to be highly correlated, so I selected the 1 kilometre radius to minimise overlap between neighbouring landscapes. Now I'll move on to my results. Overall, I conducted 1,500 bird surveys, where I recorded 76 species, including 71 natives and 5 exotic species. The most commonly recorded birds included the noisy myna, Australian magpie, common or Indian myna, spotted turtle dove, red wattlebird, little raven, rainbow lorikeet, and the grey butcherbird. All 8 of these species were recorded in over 20% of my surveys at more than 180 sites and were present in all 30 landscapes. To model the data, I split the 76 bird species into 5 response groups. These included native species, which were further broken down into aquatic species and terrestrial species. A subset of the terrestrial species then appeared in the vegetation-dependent species. Birds were deemed to be vegetation-dependent if they relied upon remnant native vegetation, such as woodland, forest, and heathland habitats. Birds were classified as woodland if they appeared on 55% of lists analysed by Fraser et al. And were classified as woodland-dependent by Radford and Bennett. The final group were the exotic species, which are introduced to Australia. For my modelling approach, I used generalised linear models to test 4 key hypotheses. Firstly, that species richness would be influenced by the housing cover within a landscape. Secondly, that it would be influenced by canopy tree cover, composed of both total tree cover and the proportion of exotic tree cover. Third, species richness would be influenced by landscape composition, including the cover of riparian areas and open green space. And finally, avian species richness would be influenced by the surrounding region or landscape context, including the mean annual rainfall and cover of native bushland within a 1 kilometre radius. I used the R package Newman to run all possible variations and selected the best model based on AIC values. So, what did the modelling show? For both natives and terrestrials, housing cover came out as a significant variable. These plots show the percentage cover of housing on the x-axis and the species richness of the bird group on the y-axis. They were generated by holding all variables except housing cover constant at the mean value. On the left, we have the native birds, and on the right, the terrestrial birds. As you can see, for both groups, housing cover has a strong negative relationship on species richness. Importantly here, the R-squared value for both models was over 0.8, suggesting that they are explaining over 80% of the variation observed in species richness. For aquatic species, both housing cover and tree cover were significant variables. Both of these variables had a significant negative relationship on the richness of aquatic birds. For vegetation-dependent birds, they were found to have a significant relationship with housing cover and the extent of native bushland within a 1 kilometre radius. Housing cover on the left had a negative relationship with vegetation-dependent richness, whereas the extent of surrounding native bushland had a positive relationship. This model had the highest R-squared of any group, explaining over 82% of variation in the data. Finally, for exotic species, there were no significant predictor variables, indicating that these species are not influenced by any of the landscape measures in my study. Rather, exotic species appear to be ubiquitous and fairly uniform across the study area. It appears that housing cover is a significant driver of species richness in urban areas. When interpreting these results, however, it's important to consider what housing cover really represents. It's a measure of urbanization intensity, and therefore a proxy for human infrastructure and anthropogenic disturbance. This includes the extent of impervious surfaces, which relates to the urban heat island effect, artificial light at night, anthropogenic noise, pollution and litter, human population density, the presence and density of domestic predators, and the density of vehicles, which relates to car strike. There's a lot going on in urban ecosystems, so it's difficult to know what exactly is driving this negative relationship with species richness. It was surprising to note that tree cover didn't have a stronger influence on bird richness. To better understand this result, we need to consider what makes tree cover valuable for birds. Tree cover quality may well be linked to food resources or the availability of nesting habitat. It may also be a question of spatial configuration, where patches of trees hold greater value than linear strips of street trees. Finally, tree origin may be particularly important for birds. I tried to account for this by including the proportion of exotic tree cover, but perhaps the difference lies between Australian native and locally indigenous tree species. In conclusion, my analysis suggests that housing, not habitat, is the strongest driver of avian species richness in urban areas. Housing cover was found to be a significant predictor for native, aquatic, terrestrial, and vegetation-dependent species. Vegetation-dependent birds also showed a significant positive relationship with surrounding native bushland. Retaining patches of remnant bushland in our suburbs may therefore help woodland, forest, and heathland species to persist, resulting in greater bird diversity in our cities. If you'd like to continue the conversation, please feel free to reach out on Twitter or via this email address. I'd like to acknowledge my supervisors, Professor Andrew Bennett and Dr. Angie Haslam, and the generous organisations who funded my research. Thank you for tuning in, and I hope you enjoy the conference.